Welcome back. Welcome back. All right, so today we'll be going over just some practice problems of actually some of the syntheses using the metal catalyzed reactions we've done. Okay, so for our first problem right here, so this will be on the Wednesday's worksheet. We'll be doing problem 1A. So in this case, we have some kind of boron that shows up right here, some boron group, and then somehow we can get to this structure right here, where this entire group right here, so two O's and then this carbon chain have been added onto where this benzene was. Okay, so one of the first things we want to do in this retrosynthesis is actually look to see if there's any special reagents that we see in this. Well, in this case, this is a boron, so we know at some point, if there is a boron in here, that there has to be some kind of Suzuki coupling. So that's one clue. We'll keep that in mind, but everything else, okay, well, there's nothing much else to see. Okay, so looking at this retrosynthesis. Okay, from Suzuki coupling, somehow we had to add these two O's right here onto this chain. Well, one of the ways that we can get these two ketones, in this case, from this chain right here, is from alcohols, by oxidizing alcohols. And so what I mean by that is, well, instead of having those ketones, we turn those ketones back to OH groups. So that's one way to look at how you can create these things. Now, going from this step over back to here, well, that's just a simple oxidation using some PCC. Again, this is retrosynthesis, so we're going backwards. All right. Now, the real question is, how did we get these two OHs next to each other? Well, if we look back, if you think back to what we talked about in previous quarters, one of the best ways that we can add two OHs next to each other is by using osmium tetroxide and some sodium hyposulfite. And this will add two OHs to each other across an alkene. So in this case, an alkene that looks like this. Okay, we're getting very close. This is exactly what we wanted. Because remember, out of all of these reactions, somewhere we had to do Suzuki coupling. And well, what's needed for Suzuki coupling? Well, looking back on here, well, we need not only the C-double bond, but we also need some kind of vinyl halide right here. Well, the good thing is we have this boron species. So going through so if we know what our boron species is, which is the original reactant, which is this group right here, then we know that one of our last reactant will just have to be some Cl. It could be Br. And again, we count the carbons. So 1, 2, 3, 4, 5. And so this entire steps right over here, going backwards is our total synthesis. So let's keep in mind, let's see what we did. Okay, so we did Suzuki coupling plus some vinyl halide, so some boronate plus a vinyl halide to get to this C-double bond right here. From that C-double bond, we use osmium tetroxide to add the two OHs next to each other on the ring. And then we use PCC in order to get to these ketones right here. All right. Okay, let's do our next synthesis right here. Now this is a little bit tougher one because now we need to keep in mind other parts of this reaction. Okay, so starting from this, just some benzene ring right here, a single benzene ring in fact, we can get to something with two benzene rings. Interesting. But also, if you noticed, there's some OCH2 groups on here. That's something to keep in mind. But we've also added two carbons right here and an epoxide. Okay, so that epoxide gives away certain facts about this. But let's see what we can do from here. Okay, so starting from the retrosynthesis. Well, the only way we can get an epoxide, the only way we can get it is from a double bond. So that's how you want to think about it, right? A CC double bond, how we can get this epoxide. And how can we get from that epoxide to the C-C double bond? Just drawing this. Well, we can get there just using MCPBA. Okay, well, that's great. Yeah, this is a pretty solid reaction so far. Okay, now this is the part where it requires a little bit of imagination. Now, granted, this original C3 group doesn't have anything on it. And unfortunately, we didn't learn reactions to add boron, so we can't use borons. We can't add tin. And other reactions, however, we can use other chemicals. But the only other one we can think about is an alkyne. So we can add alkyne, a terminal alkyne. So this double bond right here might come from a terminal alkyne. Now, that might seem unintuitive, right? So it might have come from some alkyne that looks like this. Can't draw. Let me just redraw that. Okay, all right. Like this. Now the real question is, how did we reduce this alkyne to an alkene and make it trans? Well, this is a reactant that, you know, not many people remember. But if you use sodium and ammonia, you can turn that alkyne into an alkene. Okay, that's pretty good. All right, so we got this far. This far so far. All right. Okay, so now we need to see how we can make this benzene ring attach onto this alkyne right here. Well, one of the ways we can do that is by having, again, we need to attach to 2 of these benzene rings. Well, what if our alkyne had both terminal carbons at the end, right here? Okay, in that case, if it has both terminal carbons, then what our original product of the benzene rings had to have is just a single one of those. Except this time, instead of using one equivalent of these, we used 2 equivalents because there's 2 of these benzene rings on each side. And again, we also have 2 reacting sites on these terminal alkynes. So we can add 2 of these together to make this linear form. And we can do that possibly using the Castro-Stevens approach. So in this case, Castro-Stevens, and we can use that copper plus, copper metal, and let's try triethylamine right there. Okay, we're almost done. Now, remember what our original reactant was, right? It's just a little benzene ring. So how do we add a bromine to it? Well, again, one of your reactions you learned back in 8B, Friedel-Crafts bromination. Well, in that case, we get our final product, or well, our initial product right here. And again, we use 2 equivalents of that. And so in order to go to this reaction forward, we go all the way up here, go back around over to here. So this is the general retrosynthesis of this molecule from this one right here. Okay, last problem. Now this one is pretty simple, just multi-step reactions. Okay, so our first step, we add bromine. Our second step, we add 2 moles or 2 equivalents of this super strong base, NaNH2, and some heat. And the last step, well, it just uses some vinyl halide, and it uses copper iodate, palladium, and some base. So this reaction, let's just name it. Well, in this case, this reaction right here is going to be a Sonogashira reaction. Okay, but let's actually go through the steps and see what we did. Okay, so our first step, right here. Adding the bromine. Well, we know how to add bromine across a double bond. Well, all that does is just adds 2 bromines. Okay, that's not too bad. But the next step right here, NaNH2, 2 equivalents of those, and heat. Well, the thing is that if we add base to this, some of the most basic H's or acidic H's on here are going to be right there. And we add super strong base. So if we do this, since we're adding a base, we can do a double elimination onto here, making this alkyne. Again, this will be 1, 2, 3, 4. 1, 2, 3, 4. So that's what this basis step right here does. These 2 equivalents. Okay, we made that alkyne, so that's pretty interesting. But then the last step, we add all of these reagents right here. I'm not going to write it out just for the sake of it. Well, if you remember, this is Sonogashira. So we have a terminal alkyne here, and we have this bromine group right here. So I'll just draw this again. Well, wherever this bromine was, wherever this terminal H was right here, we add them together, creating our final product of this. Now, counting carbons, we have 1, 2, 3, 4. Let's say this is 5, 6, 7. Now this is 1, 2, 3, 4, 5, 6. Sorry, my bad. 1, 2, 3, 4, 5, 6, 7. And so this is our final product at the very end, a 7-carbon system right there.